In this video, we'll be covering content from your Chapter 4, Section 3 lecture notes. We're still solving systems of linear equations, but now we'll be adding the addition method, also known as the elimination method. When we use the addition method or elimination method, the two equations are combined into a single equation. And this new equation will only have a single variable. Let's take a look at example 1. In example 1, we have two linear equations, and we're just going to start by adding them together. Adding these two equations together means that we will add all of the terms on the left side together and all of the terms on the right side together. On the left side, we have a positive 3x and a positive 5x for a total of 8x. We have a negative 2y and a positive 2y, which add to 0. On the right side, we have a negative 18 and a positive 2 for a total of negative 16. Now we have one equation with just one variable. We can now solve for x by dividing both sides by 8. And when we do that, we find that x is equal to negative 2. Substituting negative 2 back into one of the original equations, we can solve for y. This becomes 5 times negative 2 plus 2y equals 2. 5 times negative 2 is negative 10. And adding 10 to both sides, we have 2y equals 12. Finally, dividing both sides by 2, we have y equals 6. Putting this together, we have the ordered pair negative 2, 6. And that's the solution to this system of linear equations. Notice that by adding these two equations together, we were able to eliminate one of the variables. This was because we had the same coefficient with opposite sign. Let's go on to example 2 and see how to handle this when we don't have that situation. In example 2, we will again use the addition method. If we just simply add these two equations together, notice that neither of the variables will cancel out. But think about if we were to multiply this first equation by a positive 2. If every term was multiplied by 2, we would have a positive 8y and a negative 8y that would cancel out. So let's take this first equation and multiply each term on both sides of the equation by positive 2. This gives us a new equation of 12x plus 8y equals negative 108. Lining that up with our second equation, we now see that the y terms will cancel out when we add them together. We have 12x plus 3x for 15x, positive 8y and negative 8y equaling 0, and negative 108 plus positive 33 for negative 75. Now we can solve for x. Dividing both sides by 15, we find that x is equal to negative 5. Now that we know that x is negative 5, we can substitute that back into one of the original equations and solve for y. Let's substitute into the second equation. This becomes 3 times negative 5 minus 8y equals 33. 3 times negative 5 is negative 15. And adding 15 to both sides, we have 8y is equal to 48. Finally, dividing both sides by negative 8, we find that y is equal to negative 6. This gives us the ordered pair negative 5, negative 6. And that's the solution to this system of two linear equations. Once again, in example 3, if we were to simply add these two equations together, we would not have a variable cancel out. Also notice that this time we don't have one term that's a simple multiple of the other. So this time we'll need to manipulate both equations before we add them together. Let's work on trying to eliminate x. We can multiply the first equation by negative 3 and the second equation by positive 2. This will create a positive 6x and a negative 6x that will cancel out. First, let's take this first equation and multiply everything by negative 3. This gives us a new equation of negative 6x plus 21y equals negative 69. Now let's take our second equation and multiply everything by positive 2. This gives us a new equation of 6x plus 8y equals negative 76. We can now take these two new equations and know that our x terms will cancel out. Let's add these two equations together. We now have a negative 6x plus a positive 6x, which equals 0. We have a positive 21y and a positive 8y, equaling positive 29y. And on the other side, we have a negative 69 plus a negative 76, totaling negative 145. Simplifying and dividing both sides by 29, we find that y is equal to negative 5. Now that we know that y is negative 5, we can substitute that into one of our original equations and find x. If we substitute y equals negative 5 into the first equation, we have 2x minus 7 times negative 5 equals 23. That's 2x plus 35 equals 23. Subtracting 35 from both sides, we find that 2x is equal to negative 12. And that tells us that x must be negative 6. Putting this all together, we have the ordered pair negative 6, negative 5. And that's the solution to this system of linear equations. Let's again follow the same steps to solve example 4. We don't have a pair of terms that when added together will eliminate a variable, but we could multiply this first equation by negative 2, which would take care of that problem. Multiplying each term in this equation by negative 2, we have negative 8x plus 6y equals negative 42. Adding that together with our second equation, you can already see that something different is going to happen. We have a negative 8x and a positive 8x, which add to 0. We have a positive 6y and a negative 6y, which add to 0. And a negative 42 plus a positive 42, which add to 0. So we've come up with a statement that is always true. This means that we have a dependent system. And dependent systems have infinitely many solutions. We now need to express all ordered pairs that are solutions to this system. What we can do is solve our first equation for y and then express y in terms of x. Taking our first equation, we can subtract 4x from both sides and divide everything by negative 3. Now we've written y in terms of x, and we can express all ordered pairs that are solutions to this dependent system as x, comma, 4/3 x minus 7. Let's go on to another special case. Once again, in example 5, we don't have terms that would cancel out if we simply added these two equations together. But we can take our first equation and multiply by 5, while we take the second equation and multiply by 2. This would cause our x terms to cancel out. Multiplying each term in the first equation by positive 5, we have negative 10x plus 30y equals 50. Multiplying each term in the second equation by positive 2, we have positive 10x minus 30y equals negative 60. Can you recognize what's going to happen when we add these two equations together? We have a negative 10x and a positive 10x, which add to 0. We have a positive 30y and a negative 30y, which also add to 0. But on the other side, we have a positive 50 and a negative 60, which add to negative 10. This gives us a statement that is always false, no matter what x and y are. This means that we have no solutions. This is an inconsistent system, and an inconsistent system has no solutions. Moving on to example 6, we have the case of two linear equations, but there's some fractions involved. This can make it a little more difficult to figure out what to multiply each equation by so that one of the variables cancels out. Instead, let's clear the fractions by multiplying by the least common multiple of the denominators. We'll take this one equation at a time. Looking at our first equation, we can clear our denominators by multiplying both sides of this equation by 12. This gives us 12 times 2 over 3x plus 12 times 5 over 4y equals 144. 3 goes into 12 4 times. So this first term becomes 4 times 2x, or 8x. 4 goes into 12 3 times, so our second term becomes 3 times 5y, or 15y. Now we have an equivalent linear equation without the fractions. Let's do something similar to the second equation. To clear this fraction, we can multiply each side by 2. Now we have 2 times x minus 2 times 7 over 2y equals negative 50. With these 2's simplifying, this becomes 2x minus 7y equals negative 50. Again, an equivalent equation, but without the fraction. Now we'll take our 2 new equations and solve our new system. With this new system, if we were to simply add these equations together, we would not have a variable cancel out. What we can do, though, is take this second equation and multiply each term by negative 4. This will create a negative 8x, which will cancel out with the positive 8x in the other equation. Adding these two equations together, we have 0 plus 43y equals 344. Dividing both sides by 43, we find that y is equal to 8. Now that we know that y is equal to 8, we can substitute that into one of our original equations and solve for x. Let's use the second equation because the x doesn't have a coefficient. Plugging y equals 8 into this equation, we have x minus 7 over 2 times 8 equals negative 25. 2 goes into 8 4 times, so this simplifies to x minus 28 equals negative 25. Adding 28 to both sides, we have x equals 3. We finally have the ordered pair, 3, 8. And that's the solution to this system of 2 linear equations. The way that we cleared these fractions also works with decimals. We can multiply by 10 or 100 to move our decimal places over and work with integer coefficients. And that will conclude this lesson from Chapter 4, Section 3.